Thank you, viewers. This is Mr. Dingo, and I want to welcome you to the lesson of today. You remember last time in our mathematics class we were talking about differentiation. Today we are talking about part of differentiation, that is how to determine the stationary point called point of inflection. We know that we have looked at stationary point, the first one, that is the turning points. Today we want to look at the point of inflection. And a point of inflection, we are going to realize that if I do a sketch of this nature, on the sketch here, this is y-axis, this is x-axis, y-axis is there. If a point of inflection is a point where the gradient changes from positive, 0, positive, the gradient in that manner. So we can say that at this particular point here, the gradient is 0. And then it moves from 0 again to positive, because now this thing is here dy dx will be positive. Dy dx will be positive. Here dy dx will be 0. And here dy dx will be positive again. So you realize that in such a case we are not having what a turning point. A turning point, the gradient should be turning from positive, 0, negative, or negative, 0, positive. But in this case the turning point, the point of inflection is a point where we expect the gradient to move from positive, 0, then to positive again. Or it can be the opposite of that, where we could expect something like this. In this manner, it is turning from negative, 0, negative. So this is curve A, this one is curve B. So both curve A and curve B represent a point of inflection, where this one is negative here, the gradient is negative at this point, up to this point. At this particular point here, the gradient is 0. Then on the other side, the gradient remains negative. Now let us look at an example which can confirm to us that this is a point of inflection. So we have an example here, y equals x cubed minus 3x squared plus 3x. In this particular example that I've given here, we are required to be able to determine the coordinate of the turning point. After determining the coordinate of the turning point, we need to show that it is a point of inflection. So if I want to determine the stationary point, usually we know that at the stationary point, dy dx is 0. So what is dy dx of this particular function here? Dy dx of this function will be, this is 3x squared minus 6x plus 3. So we know that if dy dx is equal to 0 at a stationary point, then it means that at a stationary point, this expression 3x squared minus 6x plus 3 should be 0. So if we try to solve this equation, if we try to deal with this equation, what do? We say the product here is 9 and the sum is negative 6. So it means that the numbers that can give us a product of 9 and a sum of minus 6 should be the numbers negative 3 and negative 3. So we'll say this is 3x squared minus 3x plus 3 equals 0. Group these two. This will be 3x into x minus 1 minus 3 into x minus 1 equals 0. So we can say that this is 3x minus 3 into x minus 1 equals 0. If we have these 2 points where we have this, we can say therefore that 3x minus 3 equals 0, or x minus 1 equals 0. In this case, x equals to 1 or x equals to 1. So we realize that we don't have 2 points. We don't have 2 coordinates. We only have one coordinate here, which is x equals to 1. So this graph here, our curve here, is stationary at x equals to 1. If x equals to 1, we can be able to determine the other corresponding value of y. So y equals x cubed minus 3x squared plus 3x. If you substitute 1 where x is, we'll get y equals to 1 cubed minus 3 into 1 squared plus 3 into 1. So this is 1 minus 3 plus 3. So that is, if you have 4 here minus 3, we get 1. So therefore we can say that the stationary point in this case is 1 for x and 1 for y. So this is the stationary point. Now let's determine whether this stationary point is which kind of stationary point. Is it a turning point or is it a point of inflection? So we can use neighborhood test, where in the neighborhood test we go for the first one should be x value, dy dx, and then the last one should be shape of the graph. In this case, x, if I give 3 columns, the value of x I start with is 1 here. Below 1, I'll take a number just below 1 will be 0, and then just above 1 will be 2. If I take that and I substitute 0 in the gradient, I will get, if I substitute that 0 in the gradient here, I should be able, this is 0 minus 0 plus 3, I will get 3 here, positive 3. But if I substitute 1, I know it should be 0 because our 1 here gave us 0. What about if we put 2 here? If put 2, this will be 3 into 2 squared minus 6 into 2 plus 3. This is 4 times 3, 12, minus 12 plus 3. So this is also plus 3. So what we can see is that the shape of the graph here is positive. So the shape will be like that. Here, positive. This will be flat, and then that will be positive again. So you realize that what we have there is a shape like this. It is going this way, then flat, then that way. This is a point of inflection, and therefore not a turning point. A turning point, we expect the gradient to turn this way or that way. That is a turning point. But in this case, we can see the shape that is appearing here is a turning point. Exactly the shape we have here, where we have a positive slanting. It's positive here, it's 0 here, then it's positive again up there. Now, this is one way of testing whether it's a point, which type of stationary point you have, the neighborhood test. We can also use the second derivative. The second derivative, we differentiate the gradient function again. So the second derivative, d squared x over dx squared will be, if I differentiate this one once more, it will be 6x minus 6. So 6x minus 6, and at the value where x is 1, what do we expect to get? We'll get 6 into 1 minus 6, which will be 0. So you realize that we said that when the second derivative, dx squared, is 0, that is a point of inflection. But when d squared y over dx squared is less than 0, it's less than 0, this one should be a maximum turning point. That's why we say that when you get a negative second derivative, you have a maximum turning point. But when d squared y over dx squared is greater than 0, then you have a minimum turning point. That's why you're saying that a positive turning in the second derivative gives you a minimum turning point, sorry. So these are rules guiding if you decide to test for the turning point or stationary point using the second derivative. But you can also use the neighborhood test, which is commonly examined at your level. So viewers, that is how you deal with the point of inflection, and please, we are going to move to the next level, which is how to curve sketching. This is a very important area, and mostly students are afraid of this particular part here. And today we want to see how to make it much more simpler for you when you are doing curve sketching. And when you know this one you have done in Form 3, where you are asked to plot a graph of either quadratic graph or a cubic curve. And so when we are going to do curve sketching, we are not going to really plot accurate values. So we just need to look at a few points, that is the intercepts and the turning points. Once you have all those points, then everything is okay. So there are a few steps you need to follow when you are doing curve sketching, and you just need to do three things. One of the things you need to do is to get the y-intercept, and usually you expect to have only one y-intercept unless you are dealing with a circular curve. If you are dealing with a circular curve, then you expect to have probably two. But we're dealing with a cubic curve or a quadratic curve, you expect to have only one y-intercept, meaning the curve can only intersect the y-axis at one particular point. The other thing you need to get is the x-intercept. Now, the x-intercepts, you may find many of them, probably 2 or 3 or 4, based on the nature of your curve. Another thing you need to do here is, the final thing is to get the stationary points. The stationary points, stationary points. And once you get these stationary points, it's also good to get their nature, meaning you need to know whether a point is either a maximum turning point, a minimum turning point, or a point of inflection. So learner, once you have all these three things, then probably sketching the curve will not be a big deal. So I want us to look at an example, step by step, just the way I've listed these items, and let's see whether it's going to be a really big challenge for us to do. So the example I have here is, we are asked to sketch example 1. Example 1 here is sketch the curve. Sketch the curve of the function y equals x plus 1 into x minus 4 squared. So viewers, we are asked to sketch this particular curve here, and for us to sketch this particular curve, we are going to follow these steps. We are just going to follow these steps. Let me say this is step 1, step 2, step 3. Once we get all those steps, then our step 4 will be simple. Sketch the curve. Sketch the curve will be our step 4. Then we finally finish the question. So let us start by step 1, which is the y-intercepts, getting y-intercept. And I said earlier, if you have known in Form 2 what a y-intercept is, it must be the point where the function intersects the y-axis. And at the point where the curve intersects the y-axis, that particular point, the value of x is 0. So if we know that at y-intercept, x equals 0. So we are going to substitute 0 where x is, and that I've said is 0 plus 1 into 0 minus 4 squared. That will be 1 times 0 minus 4 is minus 4. Minus 4 squared is 16. So 16 times 1 is 16. So it means that the curve will cut the y-axis at the value 16. So the coordinate of this point will be 0, because the value of x is 0, 16. That is the y-intercept. Step 2, we said we are looking for the x-intercepts. We are looking for the x-intercepts. And the x-intercepts, you have said, again, at the x-intercept, the value of y is 0. At x-intercept, y is 0. So then I can say that x0 equals, and this 0 represents the value of y here. We have said that the y is 0 at the x-intercept. So 0 equals x minus 1 into x minus 4 squared. So we are saying this is plus. We are saying that if we have this particular expression to deal with, we can say 0 equals x plus 1 into x minus 4 into x minus 4. So we know that if we are multiplying three numbers, then one of them could be 0. That one which could be 0 we don't know. So we are just going to say either x minus 1 equals to 0 or x minus 4 equals to 0. X minus 4 equals to 0. We know that x minus 4 and x minus 4 is one thing. I'm not going to write both of them. It's a waste of time. So we are saying that x could be 1 or x could be 4. That is, this was plus 1. Don't know why I keep on forgetting that. Plus 1, so this is x equals to minus 1 and x equals to 4. These are the x-intercepts, but their coordinates could be, we know that the value of y is 0, so could be negative 1, 0, and 4, 0. So we expect our graph to intersect the x-axis at these two coordinates. Then we are finished with step 1. Step 2, we are going to step 3. Step 3 we said we are looking for stationary points. And because here we are talking about probably a cubic function, we are looking at the turning points, stationary points. And this one I've said is turning points. Viewers, we realize that this thing is taking time. We are taking really a long time developing the items we need to be able to solve this problem. So the next thing, we are going to find the stationary point. For us to find the stationary point, we need to expand this function so that we have one function we can differentiate. So I'll say y here equals x plus 1 times, let me expand this. This will be x squared minus 2 times 8 minus times 4, 2x times negative 4 minus 8x plus 4 squared is 16. Viewers, what I've done is simply to open this particular expression here, because it is x minus 4 squared, so that is x minus 4 times x minus 4. If you expand that, you will find this one here. So I'll go forward to say that this will be x into x squared minus 8x plus 16 plus 1 into x squared minus 8x plus 16. Then we move forward to expand. This is x cubed minus 8x squared plus 16x plus x squared minus 8x plus 16. So what we are doing here, y equals, let's collect like terms, x cubed minus 8x squared plus this will be minus 7x squared. 16x minus 8x will be plus 8x plus 16 equals 0. That is what we have. That is what we have as the, not 0, 0 is not here, sorry. That's what we have as the function. So if we have this one, for us to get the turning point, we need to get dy dx. So dy dx of this function here is 3x squared minus 14x plus 8. We know that at a turning point or at a stationary point, the gradient is 0. So dy dx will be 0 in this particular case. So what we are going to do here is, let's look for the numbers that if you multiply, we get product of 24, and if we add, we get a sum of negative 14. I will try negative 12, negative 2. Negative 2 times negative 12, you get positive 24, and negative 2 minus 12, you get negative 14. So we get 3x squared minus 2x minus 12x plus 8 equals 0. And if I factorize this 2, I'll get, what's common here is x. Say x into 3x minus 2 minus, what is common here is 4. So I'll take 4 into 3x minus 2 equals 0. So this will be x minus 4 into 3x minus 2 equals 0. We have that. So when we solve for x in this case, we'll get x equals to 4 or x equals 2 over 3. Those are the values of x, viewers. Now we have not finished. We are still almost halfway, step 3. So after we get the values of x for each case, we need to be able to get the coordinates, full coordinates, meaning we need to get the value of y. So the value of y, again, we know that our function is simple. Our function y is 1 x plus 1 into x minus 4 squared. So if I want to get the value of y when x is 4, y will be 4 plus 1 into 4 minus 4 squared. So what we need to get here is that this is 0. 0 squared is 0. 0 times this is 0. So it means that the coordinate, y coordinate there is 0. So we are going to say the coordinate here is 4, 0. This is one turning point. The second turning point, when x equals to 2 over 3, y will be, this will be x is 2 over 3 plus 1 into 2 over 3 minus 4 squared. So what do we have here? This is 1 and 2 over 3 times, this should be 2 over 3 minus 4. 2 over 3 minus 4 should be negative 3 and a third squared. Now let me do something about these numbers. This times this is 3 plus 2 is 5 over 3 times this is negative 9. Negative 9 over that, this will be shift, that will be 10 over negative 10 over 3 squared. So we are going to have 5 over 3 times 100 over 9. 100 over 9, we get 500 over 27. So 500 over 27, if we simplify, 500 over 27, we get 18 and 14 over 27. So we have the other coordinate. And that coordinate therefore will be 2 over 3, x 2 over 3, 18 and 14 over 27. That is one coordinate. So viewers, we are finished with step 1, which was getting the y-intercept. We got the y-intercept, which was 0, 16. We got the x-intercepts, which we said there are 2 here, negative 1, 0, 4, 0. Step 3, the stationary points, which is 4, 0. Another stationary point is 2 over 3, 18, 14 over 27. The next thing that remains for us is to sketch the curve. And to sketch the curve, let us see what we are going to do. I will have to rub this, viewers, so that we see what is going to happen. We are going to sketch the curve. We are not going to draw a curve. We are going to sketch the curve. So sketching the curve here, you need to draw the axis using a ruler. So that's what you do. If you're doing that, this x-axis, this is y-axis. Let us see what happens. We know that I need to mark this point negative 1. I'll say this is my negative 1 here. If that's negative 1, 0, I need 4. 4, 0. So if this is 1, 2, 3, 4, this is 4, 0, where I need it to be. I need to mark also the y-intercept, which is 16. So 16 along the y-axis. I know this is small, but since we are sketching a curve, let me say my 16 is somewhere here. 16, assuming we label the y-axis differently. 1, 2, 3, 4. So you can say this is 4, this is 8, 12, 16, 20. But I don't need to indicate that. Okay. So now that we have identified the intercept, one is here, it is here, this one is here, the y-intercept, which was 0, 16, is up there. We are now going to identify the turning points, and the turning points we have said they are two. One of them is 4, 0, and another one was 2 over 3, 18, and 14 over 27. These were the turning points. But there's something we have not done with these turning points. We don't know which one is minimum and which one is maximum. So let me just do that one briefly here. If I test one, I'll be able to know what the other one is. I'll just go for testing for 4, 0. 4, 0 using neighborhood test. Using neighborhood test. What is 4, 0 using neighborhood test? Let's see. Is it the minimum or the maximum? X, dy, dx, and then shape. 4 at 4 is 0. The dy dx is 0, we know that. So what about at 3 and at 5 here? So we know the dy dx is given to us there. So let me see. That is 3 into 3x squared minus 14 into 3 plus 8. That is negative 7. Negative 7. What about if it is 5? It's 3 into 5 squared minus 14 into 5 plus 8. I get positive 13. So we can see that the gradient here at this point, the gradient is negative. Negative, the gradient should go this way. So we should expect something like this. At this point it should be 0, at positive should be there. So we are expecting that something like this at this point and something as like this, because if one is a minimum turning point, the other one must be maximum turning point. So I expect the minimum turning point to be here and the maximum turning point to be somewhere. Let me say if this is 1, 2 over 3 to be somewhere here. 2 over 3, 18. If this is 20, so 18 point something to be somewhere there. Let me say that is where the point is, and the other turning point is here. And we have said that since this one will turn this way, the other one will turn this way. So let me first of all make a turn there, where that curve should be. A turn should be this way. Remember, we are sketching a curve, so don't expect my graph to be as smooth as you would expect it to be. I expect yours to be better than mine. There. So I have a part of the curve there, and this one I know the curve must pass there, then it must pass here also. So we'll come there and sketch it that way. Let it pass there. So viewers, this is the sketch of the curve that we have. We can see the things that we got are all used. The intercepts are used, the turning points are used, the y-intercept is used. So here, to ensure the examiner sees what I'm seeing, because no one can read what we have sketched here, I will indicate the turning points, which is 2 over 3, 18, 14 over 27. That is one coordinate, and the other turning point, since it is here, I will not have to really indicate it, because you can simply see it is turning at 4, 0. So I'll say this is where the graph turns. We say 4 is there. That is where the graph turns. We don't have to show it going so much high, because we don't know what happens with the other side of the equation. Viewers, this is the sketch, and what we have done from getting turning points to getting intercept, that is part of a question. So you find that when a question is set for you in examination, this part may only be around 3 marks, because the turning points you shall have gotten them and you are awarded some marks. Then you go, maybe the intercepts also have been asked from you and you have given some marks. So you just need to sketch the way it appears. Let's go to example 2, which reads the function of a curve is y equals to x minus 3 into 2x squared minus 3x plus 1. We are asked in question 1a, find the y-intercept. And we know that at the y-intercept, x equals to 0. So question A, Roman 1, we know at the y-intercept, x equals 0. Now if x equals 0 at y-intercept, what do we then find? So we take this equation, which is y equals x minus 3 into 2x squared minus 3x plus 1. We substitute x with 0. That will be y equals to 0 minus 3 into 2, 0 squared minus 3 into 0 plus 1. So this will be negative 3 times everything here is 0, 0 plus 1. So this will be minus 3. Minus 3 is the y coordinate of the intercept there. So what do we do here? We say the coordinate will be 0, negative 3. So our step 1 is done. The first question, which is 1 mark, is done. It is 0, negative 3. What we are going to do is to move to Roman 2. The question Roman 2, I will have to wrap this one. Or let me first of all start by doing it here. A Roman 2 is to get the x-intercept. And at the x-intercept, the value of y is 0. So we say at x-intercept, y equals to 0. So I'll put 0 here at the y-intercept, that is 0 equals to x minus 3 into 2x squared minus 3x plus 1. So we know that if this is the function that we have, if a number is multiplied, we multiply x minus 3 times 2x squared minus 3x plus 1, we should get 0. Then it means either x minus 3 equals to 0, where x equals to 3, or 2x squared minus 3x plus 1 equals to 0. And in this case, if we factorize, we should be able to get two numbers that if we multiply, we get positive 2, we add, we get negative 3. That should be negative 2, negative 1. So we get 2x squared minus 2x minus x plus 1 equals to 0. This and that, this will be 2x into x minus 1 minus 1 into x minus 1 equals to 0. So 2x minus 1 into x minus 1 equals to 0. So here x equals to a half, or x equals 1. So viewers, we have got 3 values. There's one, x equals to 3, x equals to half, x equals 1. So let us therefore write down the coordinates. So we'll have to wrap this one off. So the coordinates of the x-intercepts, we have 3 intercepts here. One is 3, 0. Another one is a half, 0. The other one is 1, 0. So for 3 marks, we have been able to get the x-intercept, and they are here. All of them are there. Viewers, I hope you are keeping them somewhere with me, so that we are going to need them later on. Let's go to part B of the question, which says, part B of the question, we are supposed to get the turning point. For us to get the turning point first, I want us to expand this equation so that we can be able to differentiate. The equation is y equals to x minus 3 into 2x squared minus 3x plus 1. If we expand this thing, let's go. X times 2x squared is 2x cubed minus 3x squared plus, no minus, no plus x. Then negative 3 times this will be minus 6x squared plus 9x minus 3. So y will be, if we collect like terms, 2x cubed minus 9x squared plus 10x minus 3. This is the full function that we have with us. That is the full function that we have with us. So if that's the full function that we have, dy dx of this function is dy dx equals 6x squared minus 18x plus 10. We know that at the turning point this would be 0. So let's divide each number by 2. 2 here. What do we get? We get 3x squared, x squared, sorry, minus 9x plus 5 equals 0. We have to solve this equation, and for me to solve this equation I will use a quadratic formula, and the quadratic formula we know it is x equals negative b plus or minus square root of b squared minus 4ac divided by 2a, and in this case 4.5825 plus 9 divided by 6, we should get 2.26375, or x equals 9 minus 4.5825 divided by 6, we get 0.73625. So viewers, we have got the values of x, the two values of x, 2.26375 and 0.73625. The next thing that we need to do from there is to get the values of y corresponding to those values of x. So let's move there now. And for us to get the values of y, we know that the equation is here. So we will say that if x equals to 2.263, so viewers, we substitute y here. Let me round this figure into 2 decimal places. So if you round it to 2 decimal places, we should get x equals to 2.26. That will give us easy work. Let me round it down here. So if you have x will be approximately 2.26, or x should be approximately 0.74. That would give us easy work. So here, let's deal with simplified values of x. That is, if x equals to 2.26, then what is y? Y will be 2.26 minus 3 into 2 into 2.26 squared minus 3, 2.26 plus 1. Viewers, if you do this, you should be able to get negative 3.28 as the value of y. So the coordinate therefore will be 2.26 negative 3.28. That is one coordinate. Let's go for the other coordinate. If x is 0.74, then y should be 0.74 minus 3 into 2 to 0.74 squared minus 3 into 0.74 plus 1. Viewers, if you were to do this, we will get 0.28. as the value of y, and therefore the coordinate will be 0.74 to 0.28. So we have got our coordinates, the turning points, but these turning points we don't know which one is minimum and which one is maximum. Let us go to test, and in testing we use a neighborhood test. So in neighborhood test here, let us see what we are going to see. Once we test one, we'll know the other one. This is x dy dx, this is shape. So we divide into 3. We know that it should be, let's start with this, 2.26. So if I take 2.26 as the value where the gradient is 0 here, a number bigger than this should be 3, a number smaller than this should be 2. So if we substitute that one in dy dx, and our dy dx, I think it was dy dx, if you remember, was 6x squared, 3x squared, sorry, it was 6x squared minus 18x plus 10. I think so. So if that is dy dx that we have, we should be able to, let me confirm, yeah, it should be that one. If you substitute 2 here, what do we get? 6 into 2 squared minus 18 into 2 plus 10. That is giving us negative 2. So this is negative 2. What about if it's 3? It's going to be 6 into 3 squared minus 18 into 3 plus 10. That is giving us positive 10. So if it is giving us like this, we know the shape here therefore should be this way. This should be 0, then that one should be like that. So we can tell that the point 2.26, 3.28, this should give us the maximum, the minimum turning point, and then therefore this one will be the maximum turning point. So we expect that at this particular point the graph will curve this way, and at this particular point the graph will come this way. So now that we have all the items that we need, we can therefore answer question C. And for us to answer question C, we need to bring back the items that we already calculated, the y-intercept, the x-intercept, the turning points, and so on. Let me list them down before we start. So the y-intercept, the coordinate of the y-intercept we got as 0, -3. I hope I'm right. The x-intercepts, there were 3 x-intercepts, and these 3 x-intercepts, one of them was 3, 0, another one was a half 0, another one was 1, 0, 1, 0. So we have that, and therefore right now again we have the turning points. The turning points that we have are turning points. Turning points are 2, and the first one is 2.26, -3.28. And we have said that this turning point here is minimum, so I have to indicate there. And then the second turning point is here, which is 0.74, 0.28, and we have said this one, if the other one is minimum, this one must be maximum turning point. So now that we have those turning points, viewers, we can now go ahead to sketch our curve. And sketching our curve would mean sketch is a sketch. We don't have to draw big things. And my values are going from 3, -3, half, 1, -3.28. So we are lucky. We are not going to handle very big numbers. And I'll say this is 1, 2, 3. And let me have x here, y being somewhere here. So 1, 2, 3, value 3 there. The y-intercept is -3. So 1, 2, 3. Going upwards, we're not seeing any value. We'll see what happens. On the negative x, we don't have any value. We'll see what happens. We can just have it that way. Negative 3 there, x. So let us plot the intercepts. 3, 0. 3, 0, 1 intercept is there. A half, 0. Half, 0 is somewhere there. 1, 0 somewhere there. Those are the intercepts that we have. And then the other intercept is negative 3 down here. So the turning point, let me plot those two. 2.26. 2.26, this is 2. 2.26 should be somewhere there. And that 2.26 should go with negative 3.28 somewhere down here. Somewhere down there. Then this turning point is the maximum. This is the minimum. Is the trough, the maximum 0.74, 0.5, 0.7, somewhere here, and 2.8, maybe somewhere slightly. If this is 1, this is 2, 0.28 should be around there. And it's going with 7.4. Let me say 7.4 is somewhere there. So the coordinate is there. Now we are supposed to have, the graph should come from here. It should go up. It should turn over there. After turning, it should go down. After going down, view, I hope you are following. It should turn here. It should actually turn down there. Then we should go up to where negative 3 is. So viewers, you see what we have got here is as a result of a very long process, which was first determining the y-intercept from 1 to x-intercept, which we did. You can see them here. Part B, we got the turning points, which we have here. You can see it was a long journey. And then finally, with all the things you have from part A, Roman 1, part A, Roman 2, and part B, we are able to solve the problem in part C, which is actually not a big deal. So the problem is lying here, not actually in the sketching of the curve. And that is the end of this area of curve sketching. Let's meet you next time as we look at the implications of differentiation.